Hey guys, welcome to 8.1b, nth roots and rational exponents. So this is the second lesson having to do with exponents and radicals. Some of this is going to be review, some of it is going to be brand new. So let's just go ahead and get started. Example 1 is working with the exponents. So we have 6 squared, which would be 36, 6 times 6. This one you have to be careful because it's negative 5 is in parentheses. So negative 5 times negative 5 is positive 25. But this one here, we can only square the 9. That negative is actually not being affected by the squared. So it's going to be negative 81, because you would get 81 from squaring 9, but we need to think of that sign still out there. And then what reverses squaring a number? Well, whenever you were solving for something like this, you would take the square root. That's how you undo a square. That's the idea there. Now, radicals is the other part. You've worked with radicals before, specifically the square root. But when we're talking about radicals, we're going to be looking at all kinds of roots. So there's cubed roots, there's fourth roots, fifth roots, like infinite number of roots. Some of the terminology, the number outside of the radical sign is called the index. So that's going to indicate what kind of root you're looking at. This symbol here is the radical symbol, as we've heard. And then what's inside is called the radicand. So just some terminology you're going to hear throughout the video and throughout this unit. Now, we're going to look at square roots to start. We've worked with square roots since we were probably in like 5th, 6th grade. So these should be pretty familiar. So the square root of 25, you could break that up as 5 and 5 if we do the prime factorization. We get a pair of 5s and we know it comes out as 5. This year, we learned about taking the square roots of negative numbers. It ends up being 5, because 25 breaks up into 5 and 5, but because of this negative, we have to throw that I behind it. The square root of 90 is not a perfect square, so we got to break it down. I'm going to do 9 and 10. 9 breaks down into 3 and 3. 10 breaks down into 5 and 2, but the only pair that we get is actually 3. So we end up having 3, and then what's left, we multiply back together. So 5 and 2 gives us 10. This is the simplified radical answer. We can do the same thing with 75. We would get 5 times 15 was one way we could do it. 15 breaks down to 5 and 3. So I'm going to circle my 5 since I have a pair of 5s. Pull that outside, and then I just have this 3 that goes back inside. Now, once we introduce variables, you did this in Algebra 1, but it's probably been a little while. Start with just the numbers first. So 16, that's a perfect square. We can break that down into 4 and 4. So we pull out a 4, and then we're left with a cubed. A cubed, however, if you want to think of it like this, breaks down into a squared and a, thinking about our power rules, and then a squared breaks down into a times a. So there we have a pair of a's, and then we have this lonely a here that's going to stay inside. So I'm going to pull this a out front, and I'm going to get 4a radical, and then I have a left inside, because I'm still looking for groups of 2. Same thing here. 20 we can break down into 4 and 5. 4 breaks down into 2 and 2. There's a group. So I'm going to pull it 2 outside. X squared is perfect because it breaks down into x and x. There's a pair. I get another x. And then y to the 5th we could think of as y squared, y cubed. So y squared, let me rewrite this because my answer is not going to have enough room. 2x, y squared breaks into y times y cubed breaks into y squared y, and then another y squared breaks down into y and y. So since we have 2 groups of y's that we can circle, that comes out as y squared, and then the only thing that we actually have left inside is this single y. All right, so hopefully none of that is too complicated. You have seen all of these answers before. The square root really isn't, it's more of a review than anything. The cubed roots, however, are going to be newer. I'm not sure how much you've seen with these. So just like with square roots are looking for groups of 2. Cubed roots are looking for groups of 3. So with these, start with the numbers. 80, I think of 8 and 10. 8 would break down break down into 4 and 2, and 4 breaks down into 2 and 2. 10 breaks down into 2 and 5. Since we're looking for groups of 3, you need to be able to circle 3 of the same number in order to pull it on the outside. These numbers, however, are going to stay inside. So we're going to pull out a 2, and then we're going to have this cubed root. That's our index. And then 2 times 5 multiplied back together, we get 2 times the cubed root of 10 is what this would equal. All right, let's keep going here. Now the cubed root of 81 p to the 5th m cubed. 81 we could break up into 9 and 9. 9 breaks down into 3, 3, 3, 3. So we have 3 3s that we're going to be able to pull out. Now, just a shorter way to do the exponents. I'm not trying to make it more painful than it needs to be, but we have p to the 5th. We're looking for groups of 3, so we can for sure pull out a single group of 3 p's. Okay, so we're going to get a 3. And then all that you have to do is think about how many p's would you have left inside. Okay, so since we have a 3, I'm going to write that. We would actually have p squared because we took out 3 of them as this single p, and then we would have 2 left inside. And then m cubed, we could take out all of the m's and write it as a single m, and then there's none left inside. And we just got to write the 3 here. This would be the answer. The next one, the square root of negative 125. Now, normally when we see a negative in a radical, we think imaginary solutions. But this one is not going to be an imaginary solution because, let's break up the number first. 125, we would get 5 and 25, and then 25 breaks up into 5 and 5. We get a group of all 5s. That's nice. But the answer ends up just being negative 5. Because if you think of negative 5 to the 3rd power, you actually end up getting negative 125. It's because of the odd exponent affecting the negative sign. It's okay to have an odd number of negatives when you're taking a cubed root. It's just when it's even, we can't get the same answer. That's why we have imaginary numbers to replace those. But here it's all right. Now the cubed root of positive 125, it would still break up the same way. We would see this group of 3 5s giving us 5. Okay, so let's keep going here. So with the 4th root, we are going to break this up. As you can probably imagine, we're looking for groups of 4. So 8 and 8 breaks into 2 and 4. 8 breaks into 2 and 4, and then 4 breaks into 2 and 2, 2 and 2. So in total, we have 1, 2, 3, 4, 5, 6 2s. We need 4 of them. So I'm just going to circle these first 4. And then the ones that we didn't circle go back inside, which would be these 2. I'm just going to box them. 2 times 2 is 4. So this is what our answer is going to be. And then I want to put the 4th root. So it's 2 times the 4th root of 4. Next one, we're going to keep going here. Again, looking for groups of 4. So 80, we're going to break that down into, I'm going to do 8 and 10 again. 8 breaks down into 4 and 2. 4 breaks down into 2 and 2. 10 breaks down into 2 and 5. So now I can circle 4 2s. 1, 2, 3, 4. Notice I can go to those right away. So on the outside, I'm going to pull out a single 2 since I have that single group of 4 2s. The x's, look at the number. Think about how many you can pull out. So I can pull out a single group of x's because I would end up having 4 out of that. And then if I have 8 y's, I can just divide 8 by 4 and I would get y squared because I can break that up into y to the 4th, y to the 4th. So there's going to be a group of 4 y's and then another group of 4 y's. And then what I have left is the 4th root of 5. I have a single x and then I don't have any more y's. That's going to be the answer on this one. They get more complicated the more the bigger your index is. So fourth root of 81, break that down into 9 and 9, 3 and 3. We're going to get really good at this prime factorization. And we have a whole group of 4 3's, so the answer just ends up being 3. There's nothing left inside the radical. Now this is where it gets tricky because we're back to an even number, all right? But if we do, so if I break this up into -9 and 9, and then I break this up into -3, 3, 3, and 3, it's not going to work this time because we have all these 3's. But if I were to take, so let's say -3 to the 4th power, that's going to give me positive 81. And if I were to take 3 to the 4th power with the 4th root of a -1, that's still not going to work. So when it comes to 4th roots and negative numbers, it's just going to be no real solution. And I should have put that up here too with our with this one. So yes, we would get 5i, but we are not going to worry about the i's in this unit as much. We're going to just think of this as no real solution. Our focus is going to be on getting real solutions with these because we are going to end up solving for x eventually, as we'll see. Okay, continuing on. So this is the part that's probably new to you, is the rational exponents. So the nth root of a to the x. Another way that you can write this is with a fractional exponent. So what you do is it is your base, and then it is the exponent divided by the index. So in this case, our base is a, the exponent is x, and then the index is this part here. So it's a to the x over n. That's how we could rewrite that. So let's just practice this. Rewrite the expression using rational exponent notation. So the exponent of 5 right now is just 1 because we don't see anything. So it's going to be 5 to the 1 over the index is 3. So 5 to the 1/3 power. And then we have 7, 1, and then we don't see it, but it's actually a 2 if it's a square root. This is going to be 7 to the 1/2 power. And then we have this one, it still works the same way. The exponent is 2, so it's 2 on top, and then the index is 3. Even though it's outside of the parentheses, we still consider that the exponent. And then lastly, this one would be 15 to the 7 over 4. All right, almost done here. Next one, we want to rewrite the expression using rational notation. So this time we're going to do the reverse. So remember, this is the exponent, this is the index. So we're going to write radical 3. You can put the 1 there if that helps, and then you can also put the 2. But this is the same thing as just the square root of 3. This one would be radical. The index is going to be the 3 because that's what's on the bottom, and then it's going to be 5. And you could do it one of two ways. You could put the square on the outside, or you could put the square on the inside. Or you could actually just square 20 or 5 squared, which would be 25. All 3 of these are technically acceptable. The next one would be the 4th root, because that's on the bottom, of 6 to the 1st power, or just 6. And then the last one, this is where we kind of have to be careful, okay? Because for this one, it would be the square root, or 2 on the outside, of 8 to the 5th power, or 8 to the 5th. All right, so let's try some of these without a calculator. We're going to evaluate. The 4th root of 625. So hopefully you remember this one. If not, 25 times 25, you could break it up other ways. And then 25 breaks into 5 and 5. This one breaks into 5 and 5. And then we are looking for groups of 4. So the answer for this one ends up just being 5. Now this one, hopefully right away, you're cautious of negative numbers because we're not going to be able to get a real solution for this one. So we can just put no real solution. And the reason we can't is because this is going to be a negative inside with an even index. If it was odd, we could potentially get a solution. The next one, we have the fourth root of 81. So that breaks down into 9 and 9. And this breaks into a group of 4 3s. So the solution is just 3. Now this one, when you have the negative exponent, now notice that, or not negative exponent, the rational exponent, think of this as parentheses because that negative is actually on the outside. So we have 81 inside, and then it's going to be the fourth root. We have to get good at going back and forth rewriting these. And we just did the fourth root of 81. We got 3, but because of this negative sign, our answer is going to end up being negative 3. And the reason it's okay to get a real solution this time is because the negative is outside of the radical. If it was inside, we would have written no real solution. The next one here, negative 27 to the 2/3 power. So this time, this is our index, the bottom one, so that goes out there. We have negative 27, and then what I like to do with these is if you put the square on the outside, it's going to make this way easier. Because this breaks down into a perfect, it's not going to work. But 27 is a perfect cube. It's going to break down into 3 groups of 3. But since it's a negative, it's going to end up being negative 3 in parentheses squared. Let me try and show this here. So we would get 9, 3, 9 would be 3 and 3, and then we can't forget about that negative sign. So there's our group of 3s. But once you square a negative, it becomes a positive. So the final answer ends up being 9. This time, though, notice the parentheses is not there, so we have to assume that the 2/3 is only affecting the 27. We're going to keep the negative outside, and then we're going to write 3, 27, and then this part we're going to square. The cubed root of 27, like we just saw, is going to be 3. But now when we square this, we only square the 3, not the negative. So it's going to end up being negative 9 is the answer. You can see how these can be really tricky because we go back and forth with the negatives. And now, using the negative exponent rules, we need to be able to solve these next ones. So 9 to the negative 3/2. Since this is negative, the trick here is to actually put it as 1 over 9 to the positive 3/2 and then evaluate. What this is going to equal is 1 over, rewrite it in the as the radical. It's going to be the, nope, 2's the index. It's going to be the square root of 9, and then we got to cube that. Now the square root of 9 is a nice number. It's 3, but since we got to cube it, we get 1 over 3 cubed is 27. We got to do the same thing with this one. I'm going to rewrite this as negative 1 over, bring this to the bottom, 32 to the 3/5 power. Rewrite it as the 5th root of 32 to the 3rd power. And usually these end up being nice numbers. So we get negative 1 over the 5th root of 32. You can go ahead and break it down. It's going to be 8 and 4. And we'd be looking for groups of 5, but it ends up being 2, 2, 2, 2, and you get a whole group of 2's. So it ends up being the 2 cubed, and then 2 cubed is 8. It's negative 1/8 is the answer for that one. Okay, well, that's a lot. We're almost done here. And then we can also solve the equations for real roots. Okay, the way that we do this is we isolate the power, take the appropriate root of both sides, and then continue with opposite operations if necessary. So in this one, we have the power isolated, and if this was x squared equals 25, we know we would take the square root of both sides. But in this case, it's a cube, so we need to take the cubed root. And x is going to equal, 125 is a perfect cube, so it ends up being 5. The next one, I need to isolate it by dividing by 3. So we get x to the 5th equals -1. To undo a 5th power, we have to take a 5th root. Now, since this is an odd index going into a negative number, it works. And the 5th root of -1 is just going to be -1. Continuing on here. First step with this one would be to add 3. Get 2x plus 4 cubed equals -16. Be careful when you add those two. And we divide by 2, x plus 4 cubed, because we're trying to get this parenthesis by itself, equals -8. And then to undo a cube, we got to take the cubed root. We get x plus 4 equals the cubed root of if it was positive 8, it would be 2, and then it's a negative, so then we just get -2. Then we subtract 4, and we get x equals -6. Be careful with that one, because -2 minus 4 more. Then the last one, we would add 7 to both sides. You would get x to the 4th equals 10,000. And this one, when you take the 4th root of this one, you end up getting x, because those are going to go away. And then this would break into 100 times 100. This would break into 10 times 10, 10 times 10, and then we get a group of 10s. So the answer is 10, but this time, just like when you're taking the square root of like x squared equals 25, we get x equals plus or minus 5, because either one would work. The same thing is true here, because we have an even root that we're taking, the 4. So it goes back and forth, but we have to be careful. But it does end up being x equals plus or minus 10 when we're solving. All right, go ahead and try the exit ticket that's following.